A whisper, not a beacon. We caught it near 18 centimeters right where hydroxyl lives. No modulation, no code. Just the radio trace water leaves behind when sunlight breaks it apart in a comet's coma. Those 08 lines around 1,665, 1,667 megahertzes are a standard tool in comet science. We've leaned on them for decades because the physics is stable and repeatable. In a vacuum, ice doesn't melt, it sublimates. As an icy nucleus warms, H2O jumps straight from solid to gas and fills the space around the core, the coma. Ultraviolet photons then snap bonds in that gas and build short-lived OH radicals. When OH steps between specific quantum states, it emits at to 18 centimeters. Detect that line cleanly, and you're hearing water chemistry, not intention. This pathway sublimation, photodissociation, OH emission, has been modeled and used to estimate water production rates and gas speeds in many comets. What matters first is where the line sits. The ill doublet of OA lies at to 1,665.402 and to 1,667.359 megahertzes. Across scores of apparitions, radio campaigns, for example, have catalogued these lines, building a baseline for how strong they get near perihelion and how they fade with distance. That baseline lets us tell normal outgassing from everything else, no story required. Behavior matters next. A natural coma tracks the sun, not us. As heliocentric distance shrinks, sublimation ramps, O formation strengthens. The to 18 centimeters line rises above noise. After perihelion, heating falls, production drops, the line thins and slips under the threshold. Line widths reflect gas expanding away from the nucleus. Shapes can skew if jets or vents bias the flow. These signatures are what radio astronomers expect and routinely measure when chemistry, not communication, is driving the spectrum. Hearing a comet is different from seeing one. Images give architecture, coma, dust, and ion tails. Radio weighs breath. Integrating the 18 centimeters line yields the number of OH molecules along the beam, with well-studied photochemistry that converts to a water production rate and a characteristic outflow speed. It's why OH monitoring became a backbone of comet studies from Arecibo to Nanche to the VLA era. It turns a fleeting window into numbers you can compare across objects and years. None of this requires exotic assumptions. The hydrodynamics of a sun-heated coma, how energy input, vent geometry, and porosity translate into a flow, have been worked through in detail. The result is a disciplined picture. As isolation rises, deep pockets open, vapor finds cracks, and the coma breathes faster. Radio follows that breath with fewer geometric biases than optical alone, because the beam samples a broad swath of the gas. On the visible side, tails behave by geometry, not by will. Ion tails point down the solar wind streamlines, dust tails curve along the orbit, and under the right alignment, an anti-tail can appear to point sunward, a projection effect, when Earth crosses the comet's orbital plane and sees the dust sheet edge on. It looks strange. It is ordinary physics, so we say it plainly. The detection near 18 centimeters is not a message. It is a measurement, a line at the frequency OH must occupy, a strength that follows solar heating, a profile set by expanding gas. These are the signatures that let us reject engineered structure without drama and still keep the wonder where it belongs on the fact that chemistry from another birthplace behaves like chemistry here. Meaning doesn't require a sender. A child hears the ocean in a shell. No one put it there. In the same way, the OH line carries identity, what the object is, without implying desire, what it wants. From that identity, we extract scale. Strong lines imply abundant water ice. Broader lines imply faster outflow. Narrower lines, or ones that shift over hours, can hint at rotation, vents, or seasonal patches on the surface. Each piece ties back to a physical cause we can test. There is discipline in how we listen. First, lock the frequency to the known OH doublet. Second, check that intensity tracks heliocentric distance rather than Earth's position. Third, compare line shapes to expected coma expansion models and look for jet-driven asymmetries. Finally, braid radio with optical and infrared. Radio for water production, optical for dust morphology, IR for volatiles like CO, CO2, and thermal context. Agreement across bands is the difference between a story and a standard. If the word signal pulls you towards SETI, park that for now. SETI looks for modulation, cadence, and information content. The OH line is none of those. It is nature's choice, not a communicative pick. Historically, when observers rechecked mysterious narrowband events, many wilted under replication. By contrast, cometary OH thrives on replication. It appears at the same frequencies, strengthens near perihelion, and fades on schedule. That is what confidence looks like in radio comet science. The quiet astonishment is this: the same molecular physics that works for comets born under our sun also works for a body that formed elsewhere. Water is durable. The OH line, it written at to 18 centimeters, is universal. Hearing that line isn't contact. It's continuity, the laws we know, verified in material that did not originate here. That's enough to justify the patience, the schedules, and the long integrations it takes to catch a whisper that always belonged to physics. Start with what it wasn't. No modulation, no encryption, no engineered cadence, nothing that would carry information the way transmitters do. What we heard near 18 centimeters matched hydroxyl OH, the daughter of water, after sunlight breaks H2O in a comet's coma. That's chemistry, not code, process, not intent. Now what it was: a precise, repeatable line near to 1,665, 1,667 megahertzes that rose as solar heating rose and weakened as the object receded. The profile behaved like an expanding gas, not like a beacon. It was detected when activity peaked and fell away along the expected curve afterward. Every part of that story fits a thermally driven coma. Why repeatability matters: noise doesn't repeat with physics. Sublimation is temperature dependent. As an interstellar nucleus approached perihelion, sunlight pushed water ice straight from solid to gas. That gas filled the coma. Ultraviolet photons snapped bonds and produced O. Those radicals emitted at 18 centimeters. Point a radio array during that window, and a line appears where the molecule says it must no appeal to intention required. When the heating falls, the line weakens. That is a pattern tied to the sun, not to us. What a line can tell you without saying anything. Integrated over time, the line's area maps to the number of OH molecules in the beam. Through well-studied photochemistry, that becomes a water production rate. Line width and shape constrain expansion speed and, by implication, vent geometry and surface activity. In the 3I Atlas campaign, measurements near perihelion were strong enough to set production bounds and place the nucleus within the size class of active, long-period comets. Numbers you can't extract cleanly from reflected light when the coma swamps the nucleus. So, why does a natural line feel so consequential? Because it's a first of method, not a first of contact. Before this, interstellar visitors were mostly seen in optical light curves, tails, and colors. Here, we heard one. Radio turned breath into data. That change expands what we can know on short notice, and it sets a playbook for the next inbound object. Listen at to 18 centimeters near peak heating, track decay post-perihelion, braid radio with optical and infrared for a full picture. Keep the categories straight. SETI searches for artificial transmissions, narrowband carriers with modulation, information content, or timing that survives scrutiny. The discipline lives on replication that implies intent. Famous one-off oddities tend to evaporate upon re-observation or reveal terrestrial origins. By contrast, the OH detection from 3I Atlas reappeared exactly as physics predicted, tracked the sun rather than Earth, and sat at the frequency set by the molecule. That's not a message that failed to impress. It's a measurement that did. Why not a message is not a downgrade. If the line had carried data, it would have pulled the story toward design and purpose and away from what the spectrum actually says. But a natural OH line is powerful because it is constrained. It lets us weigh out gassing rates, compare against models, and test ideas about surface porosity, jetting, and seasonal exposure without inventing motives. Confidence comes from how many ways the same explanation fits: frequency, timing, profile, and evolution with distance. Listen to the sequence in plain English. The object warmed as it approached the Sunday water, sublimated into the coma. UV light broke H2O into OH. O emitted at to 18 centimeters. Arrays detected the line near perihelion. As heliocentric distance grew, production fell and the line faded. That's the whole arc. It is not a narrative we prefer. It is a mechanism we can test. Why does the timing matter? The strongest detections clustered around late October, just when heating peaked. That alignment is a sanity check. If a transmitter were aiming at us, you would not expect the signal to care about the comet's distance from the Sunday. The OH line did care. It rose with insolation, not with terrestrial geometry. It declined after perihelion, not after closest approach to Earth. That behavior locks the cause to energy in, not to attention paid. How not nothing becomes a standard. A standard is a method that travels well. The 3I Atlas record shows that the same OH toolkit honed on home system comets applies to an interstellar body. That's an actionable lesson. Book time on radio arrays near expected activity peaks. Coordinate optical teams for morphology and photometry. Add IR for volatile context. And stitch the bands together so production, temperature, and geometry can cross-check. The result is a template that turns a brief window into durable knowledge. A brief word on expectation management. Extraordinary claims require extraordinary evidence. Doesn't mean extraordinary expectations demand extraordinary stories. It means keep the bar where it belongs. A natural OH line at 18 centimeters meets every test a natural OH line should meet, until a competing hypothesis explains more of the data, with fewer assumptions, modulation where none appears, timing structures where none exist. Occam's razor keeps us here, where the meaning lives. It lives in continuity. The water that emitted at 18 centimeters didn't form under our Sunday. It condensed in a different disk, locked its history into ice, and crossed deep time before our star warmed it. The same physics gave the same line. That sameness, verified, quantified, widens our map of where familiar chemistry persists. It tells us who the visitor is without claiming to know what it wants, because want isn't a scientific variable here, and it lives in preparation, because we turned signal into standard. The next object won't catch us flat-footed. We know when to listen, where to point, and what a natural profile should look like. We also know what would count as weird enough to justify speculation. Modulation that survives controls. Timing that resists solar correlation. Lines that wander off the molecular fingerprint. Short of that, the data already explain themselves. Say it one last time. Cleanly. Not a message, but not nothing. A line where a line should be, tied to heat, not hope, carrying enough information to weigh a breath and compare one star's chemistry to another's. The wonder is not diminished by the lack of intent. It is sharpened by the presence of measurement, not a myth. A measurement, 18 centimeters. Think of a ruler laid across the radio spectrum. At one specific tick, about 18 centimeters in wavelength, to 1,665. 1,667 megahertzes, hydroxyl OH reveals itself. That tick isn't chosen by engineers. It's set by quantum mechanics. When OH steps between energy states, it sheds a photon right there. The result is a narrow spectral line you can point to, model, and verify. For comets, that line is the natural consequence of sunlight doing chemistry. Ice in a vacuum sublimates. Water vapor expands into a coma. Ultraviolet photons crack H2O, creating OH. Those radicals emit it to 1,665.402, 1,667.359 megahertzes. Detect the line and you've detected water chemistry in action. No intent, no code, just molecules following rules confirmed across many solar system comets. Why 18 centimeters matters? It's both a fingerprint and a meter. As a fingerprint, O always writes at the same place on the dial. If you see a line exactly where OH must be and its strength and shape track solar heating and coma expansion, you're looking at physics, not a beacon. As a meter, integrating the line's area counts OH molecules in the telescope beam. Known photochemistry ties that to the water production rate. 18 centimeters lets us weigh a breath. With 3I, Atlas, the Meerkat array in South Africa, aimed at that tick mark. Near late October, 2025 perihelion, the array registered the expected 18 centimeters OH emission. Line strength and timing matched a coma at full activity. Early estimates implied thousands of kilograms per second of water release. It became the first confirmed radio detection from an interstellar comet, delivering measurements that optical images alone can't. If the signal sits exactly where the molecule says it must, why did anyone call it mysterious? Because it was the first time we heard an interstellar visitor, not just saw one. Hearing raises new questions and answers them with numbers. What the 18 centimeters line encodes without carrying a message. 1. Production rate. Q. H. 2. O. The integrated intensity scales with OH column density. Via OH-H2O relations, teams derive kilograms per second of water loss directly from the line. This is cleaner than inferring mass loss from visual brightness, which depends on dust sizes, albedo, and dust-to-gas ratios. 2. Outflow speed and coma physics. The line width and profile reflect gas expanding off the nucleus. Asymmetries can hint at jets or vents. Comparisons with solar system comets show similar expansion speeds and textbook profiles at comparable solar distances. 3. Thermal driver, not terrestrial geometry. The 18 centimeters line peaked at perihelion and faded afterward, tracking isolation, not Earth's position. That ties the cause to energy in, not to any response to us. 4. Natural band, around 1,665, 1,667 megahertzes, is a radio astronomy band, used because nature uses it. A communicative beacon would more likely show modulation or timing structures and often pick a different universal frequency. 18 centimeters didn't call us. It calibrated us frequency, profile, evolution with distance. Those three checks filter romance into rigor. Why this is foundational, not fanciful, universality across stars. Every OH radical, whether made under our sun or another's, transitions at the same energy gap. Detecting that line from 3I, Atlas confirms familiar water chemistry in material formed beyond our system. Same physics, different birthplace. Comet structure from spectra. Line behavior favors a heterogeneous, porous nucleus ice, threaded with dust and rock, letting gas escape through cracks and channels as surfaces heat. A cleaner yardstick than optics alone. Optical images show coma architecture, central condensation, ion and dust tails, and sometimes a geometry-driven antitail, but turning brightness into mass loss is slippery. The 18 centimeters line anchors those visuals with a direct measure of H2O. Together, radio plus optical convert a fleeting apparition into a reliable dataset. When the lamp dims, the line thins. Not silent sensitivity. Post-perihelion fading is the control experiment nature runs for free. Addressing common confusions, it did not appear when it neared Earth. The rise follows the sun, not us. It is not a beacon. Beacon hypotheses predict modulation, cadence, or non-natural frequency choices. Here we see a natural OH profile and smooth intensity changes with solar distance. Why not before? We lacked either the opportunity or sufficient activity. This time the object was active enough and the planning precise enough to catch the line at peak. What the line lets us prepare for. 1. Book radio time bracketing perihelion to track the rise and fade of 18 centimeters 08. 2. Cross-check with optical, IR for morphology and volatile mix. 3. Compare profiles to a growing library expansion speeds, asymmetries, decay curves. So weird is defined by data, not by vibe. This is how a single wavelength becomes a standard. At 18 centimeters, physics signs its name, and we can read it. We've anchored the event at a single universal line, the OH fingerprint, that turned a rumor into a reading. Next, we widen the spectrum. What does 3I, Atlas's volatile mix water versus CO2 versus CO say about its birthplace and thermal history? It didn't speak. It changed state. Far from the sun, 3I, Atlas, behaved like a closed archive, dark, quiet, chemistry asleep. As the inbound leg shortened and solar flux climbed, the nucleus crossed a threshold. Ice that had held for eons began to sublimate. In a vacuum, ice does not melt. It jumps straight to gas. Molecules of H2O escaped the matrix and flowed outward to form a coma, the thin, expanding atmosphere that makes a comet look larger than it is. Ultraviolet photons then did what ultraviolet photons always do. They broke water apart, creating short-lived hydroxyl radicals, OH. When OH steps between specific energy states, it emits at to 18 centimeters. That radio line is not intentional. It is the consequence of heating, dissociation, and expansion acting on schedule. The moment of audibility matched the moment of maximum heating. Late October 2025 near perihelion Meerkat registered OH emission at the expected frequencies around 1,665, 1,667 MHz. Line strength tracked the energy budget, high at peak, then fading as the object receded and isolation fell. That temporal footprint is diagnostic. It ties cause to the Sun, not to Earth, and it repeats a pattern logged for countless comets within our system. What, exactly, woke? Not a transmitter. A surface and possibly subsurface network of vents, cracks, and porous pathways that convert temperature gradients into flow. As solar radiation penetrates the upper centimeters to decimeters, pockets of volatile ice coughed awake. The coma's bulk velocity broadened the OH line. Asymmetries hinted at collimated jets versus diffuse release. Integrating the line, area turned the spectrum into counts of OH along the beam. Known photochemistry then scaled that to a water production rate. Early estimates placed the outflow at thousands of kilograms per second, big enough to measure confidently, modest enough to remain cometary. The awakening followed a familiar sequence you can narrate without ornament. Solar heating increases with decreasing heliocentric distance. Surface temperatures rise. H2O sublimates. A coma forms. Gas accelerates away from the nucleus. UV photons photodissociate H2OOH plus H. OA emits near 18 centimeters during radiative transitions. The OH line peaks near perihelion, then decays as the comet moves outward and production falls. Optical teams saw the geometry answer the radio. The gas tail, ionized and pushed by solar wind, streamed roughly anti-solar. The dust tail curved along the orbital path. Under plane-crossing alignments, an apparent anti-tail pointed sunward, a projection artifact of viewing a dust sheet edge-on. Meanwhile, post-perihelion, brief outbursts punctuated the fade. Thermal stress can fracture surface layers, exposing fresh ice and driving short spikes in brightness and gas release. None of this requires design. All of it obeys the bookkeeping of heat, momentum, and material strength. If you're recording for voice, the point to land is simple. We didn't receive a sentence. We recorded a phase change. It's the same with kettles and clouds. Input energy alters state. Altered state yields measurable signatures. With comets, radio hears the breath that optics sees. The OH line transforms a picture into a rate. The width transforms a glow into a speed. The way both evolve with distance transforms a pass-by into a physical story we can test against models. Why does the timing matter this much? Because timing is the control in nature's experiment. A made signal would not care about the comet's solar distance. A thermally driven spectrum must. In 3I, Atlas, the line rose into detectability as heating crescendoed, then fell in step with reduced flux after perihelion. That lockstep behavior is the cleanest argument available for transformation, not transmission. We can go deeper without leaving observation. Line profiles carry hints about vent geometry. Symmetric profiles suggest more isotropic outflow. Skew or shoulders can indicate jets grazing the beam or time-variable sources modulated by rotation. Cross-fading radio with concurrent optical light curves constrains whether spikes in OH coincide with optical outbursts, evidence for crust failure and fresh volatile exposure versus steady, distributed release. In the 3I Atlas record, the correspondence between radio fade and optical decline dominated, while short-lived flares sat neatly in the class of thermal stress events seen in many comets post-heating. What changed in us is method, not hope. Previous interstellar visitors were mostly optical stories, brightness, colors, shapes, and the arguments that trailed them. Here, radio extended the senses. Meerkat's array 64 dishes stitched into one ear joined the campaign specifically to hunt the OH line. That planning turned a brief window into a decisive dataset. Frequency where it must be, strength when it should be, decay as expected. Firsts matter in science not because they are dramatic, but because they become standards. There is also the deeper continuity that good measurements reveal. The water that lit the dial at 18 centimeters did not condense under our Sunday. It formed in a different protoplanetary disk, mixed with dust in a porous nucleus, and then crossed interstellar space until our star woke it. The fact that it behaved like our comets, same spectral fingerprint, same thermal coupling, same rise and fall near perihelion, tightens rather than loosens the map we keep of chemical universals. Similar conditions write similar lines. That's the point. For production, the instruction set going forward is straightforward. Book radio time bracketing perihelion to capture the full rise and decay of the OH line. Pair with optical imaging for morphology and timing of outbursts. Fold in infrared for volatile context, CO, CO2, and thermal balance. Use the OH to H, 2O relations to derive water production. Compare with line widths to estimate expansion speeds. Watch for profile asymmetries that imply jets. Treat post-perihelion fading as the built-in control that validates the thermal hypothesis. By mid-November, the cadence softened, outgassing ebbed. The coma shrank, the O-line thinned toward noise. The window narrowed, but the core result held. The voice we heard was a change of state ice to vapor, bond to fragment, fragment to photon, played on an object not born here, under a sun it never evolved to meet. That it was predictable does not make it small, it makes it science. If it were a beacon, the data would say so. An interstellar object lights up a radio line, and every reflex we've trained on decades of SETI headlines fires at once. Is someone calling? It's a fair question, so let's test it like scientists, not romantics. We'll outline what a plausible artificial signal should look like, then set those expectations beside what 3i Atlas actually did on the dial, in time and in shape. The point isn't to mock the idea, it's to measure it. When the numbers are clean, the answer usually is 2. First, what would an engineered emission likely show? Narrowband concentration with deliberate structure, repeats, timing marks, sweeps, or modulation that encodes something besides chemistry. You'd also expect a frequency choice that says universal. Think the hydrogen line at 1,420 MHz, not a band that nature already occupies for molecular transitions. And you'd expect behavior decoupled from solar heating. A transmitter need not care where the sun is. Those are the diagnostic rails. Now the record for 3i. Atlas. Frequency. The line sat exactly at the hydroxyl OH transition near 18 centimeters. 1,665, 1,667 megahertzes, a place radio astronomers use to study natural outgassing from comets and interstellar clouds. If you were choosing a hello galaxy channel, you would not hide inside a chemistry line that screams "oh" in a coma. You'd pick a cleaner, conventionally proposed marker like 1,420 megahertzes. 3i Atlas did the opposite. It picked what physics forced, not what engineers would. Time behavior. The signal rose toward perihelion and faded after, tracking solar distance and thus isolation textbook for thermally driven sublimation and photodissociation. A purposeful transmitter would not strengthen just because sunlight increased. A coma does. This lockstep correlation is one of the strongest arguments for nature over intent. Spectral shape. The profile shows the characteristic OH line broadened by expanding gas, with no modulation or cadence beyond mild variations, explainable by rotation and vent geometry. Communication signals love patterns. Gases obey gradients. We saw gradients. Crossband consistency. Optical teams watched the coma and tails behave like an active natural comet, including a geometry-driven antitail seen under plane crossing alignments. The radio told us how much water was leaving. The optical told us where the dust and ions went. Both changed in step with the Sunday. That's not choreography, it's thermodynamics. A common pushback is emotional, not empirical, but it started talking near Earth. Suspicious. The timeline refutes that cleanly. The OH line became detectable when heating peaked near perihelion. Its decline followed the fall in flux afterward. The pattern keys off heliocentric distance, not geocentric proximity. That's comet physics, not Earth drama. Another is visual. The anti-tail pointing toward the sun sparks propulsion speculation. But anti-tails are projection effects seen in many comets when Earth crosses the orbital plane. You're looking edge-on at a dust sheet stretched along the orbit, so it appears to spike sunward. 3I Atlas showed the standard pair ion, dust tails anti-solar, anti-tail a long track, exactly when geometry predicted. No rockets required. Even the erratic brightness surges land in familiar territory. Outbursts occur when thermal stress fractures the crust and exposes fresh ice, or when volatile rich pockets vent. They're normal, not narrative. 3I Atlas had them. So do plenty of long-period comets. The differences are in proportions and timing, not in category. Let's stack the artificial hypothesis against the data, point by point. 1. Would a probe transmit at 1,665, 1,667 megahertzes? Unlikely. That's the OH line, a protected, naturally occupied band. Beacon proposals for universality have historically clustered around 1,420 megahertzes, hydrogen, and nearby combinations. Picking OH at 18 centimeters hides your signal inside chemistry noise we expect from comets. 3I Atlas matched chemistry, not communication. 2. Would a transmitter's power track solar flux? No reason it should, but outgassing must and did. The intensity peaked at perihelion and declined after, fitting the known relation between heating and production. That's a natural light curve, not an intentional schedule. 3. Would we see an engineered structure in the spectrum or in time? We'd expect modulation, periodicity, sweeps, or narrow-coded subcarriers. The OH line from 3I Atlas shows none, just the smooth profile and widths of expanding gas with minor rotation-linked variability. 4. Does multiband evidence agree on a natural source? Yes. Meerkat measured O8 in 18 centimeters. Optical images saw coma, tail morphology evolve as expected. Both data streams moved in lockstep with distance from the Sunday. Agreement across independent instruments is hard to fake. It's easy when physics is doing the writing. There's a subtler reason to be cautious with Alien here. We're finally listening in a new way. This was the first confirmed radio detection from an interstellar comet, achieved because teams planned for OH and caught it at the moment it should be loudest. Firsts feel dramatic, standards feel dull. Science starts with firsts and ends with standards. We're moving along that curve. So, is there anything in the ledger that leans artificial? The burden is high. You'd need non-thermal timing disconnected from isolation, non-molecular frequencies, or information-bearing structure. None appears. Instead, we find what hundreds of solar system comets have shown us. Water sublimates, UV cracks, H2O, OH, radiates at 18 centimeters. The coma expands, and the profile widens accordingly, except this time, the water originated beyond our sun's formation. That's extraordinary enough without adding intention. Does ruling out a beacon make the story smaller? No, it makes it clearer. The clean match to OH physics tells us that familiar chemistry is operating in material from another star, tightening the case that comet formation pathways and the ices they trap are shared across systems. The alien here isn't agency, it's origin. We didn't catch a message. We caught the method, how cold bodies breathe when a new sun warms them. One last practical note for the next visitor. When the surveys flag another hyperbolic inbound, we should book radio time around its perihelion, aim at 18 centimeters, OH from the start, and watch for any departures. A line that doesn't track heliocentric distance, a profile that doesn't look like expanding gas, or a frequency that dodges known molecular transitions. That's how you keep the alien hypothesis honest. You give it a fair test and require it to win on evidence. 3. Atlas didn't. The bar remains set and reachable if nature ever hands us something we cannot fit to physics. Begin with the test, we owe the idea. If someone were transmitting, the spectrum and the clock would tell on them. Artificial signals show structure, modulation, narrow subcarriers, repeating timing marks, engineered sweeps features designed to carry information. They also tend to favor universal frequencies. Historically, proposals cluster near the hydrogen line at 1,420 megahertzes, rather than bands that nature already occupies for specific molecules. Now hold that diagnostic up to what 3I, Atlas, actually did. Frequency. The detection sat on the hydroxyl OH Le doublet near 18 centimeters to 1,667 megahertzes, exactly where OH must radiate when water in a comet's coma is split by ultraviolet light. Engineers don't pick that frequency. Physics forces it. If you wanted a beacon hiding inside a chemistry line that radio astronomers already use to monitor natural coma activity, would be a strange choice. Timing. The line rose toward perihelion and faded after, tracking isolation rather than Earth's position. That is a textbook for sublimation-driven outgassing, and precisely the opposite of what you'd expect from a transmitter whose duty cycle needn't care about the comet's solar distance. Shape. The profile looked like gas, widths set by expansion velocity, gentle asymmetries consistent with vents or jets, and no sign of modulation or beacon-style cadence. Communication signals love patterns. Gases obey gradients. We saw gradients. Cross-checks. While radio weighed the breath, optical work mapped morphology. Coma, dust and ion tails, and under the right edge on geometry a projection-driven anti-tail that can point sunward without invoking propulsion. Everything evolved in step with the sun's heating, not with us. Put plainly, the three pillars, frequency, timing, and shape, land squarely on natural comet physics. If an artificial hypothesis cannot explain more of the evidence with fewer assumptions, Occam's razor leads us to the simpler mechanism that already fits everything on the page. But simpler isn't smaller. It's harder to headline and easier to measure. Here is what the physics buys us. 1. A molecular fingerprint you can audit. OH appears at to 1,665.402, 1,667.359 megahertzes because of a fixed quantum energy gap. The same transition has underpinned comet studies for decades. Detect the line, integrate its area to count OH along the beam, convert to H2O production rate via well-studied photochemistry. With 3I Atlas, that procedure turned a fleeting window into numbers, not metaphors. 2. A clock tied to energy input, not to us. Thermal control means you can predict when the line should crest, near perihelion, and when it should thin, post-perihelion. That's exactly what the campaign saw, with the Meerkat array logging the line in late October 2025 and the signal decaying with the drop in solar flux. Nature handed us a built-in control experiment. We just had to be listening. 3. A dynamical yardstick. Line widths trace expansion speeds. Small skews hint at jets, vents, or rotation. These signatures matched what we expect at that solar distance from an active nucleus, without needing exotic thrust or guidance. Physics gave us a speedometer embedded in the spectrum, a way to fuse bands into one story. Radio turns breath into mass loss. Optical frames show where dust and ions go. Together they constrain nucleus scale, porosity, and vent geometry far better than either band alone. The consistency across methods is a stronger argument than any single plot. If you're used to SETI logic, the discipline here will feel familiar. You start with the most exotic interpretation that fits your hopes, then you ask the spectrum and the clock to argue you out of it. In SETI, that means demanding modulation that survives reobservation, timing that refuses natural drivers, and frequencies that dodge known molecular lines. With 3I, Atlas, none of those hurdles were cleared. No modulation, no beacon cadence, no hydrogen line hello, and a signal that tracks the Sunday. The artificial hypothesis didn't just lose. It failed where physics was already explaining more with less. Occam's razor is often caricatured as pick the dull option. That misses the point. The razor says, don't multiply entities beyond necessity. If thermally driven outgassing explains the frequency, timing, line shape, and crossband behavior, while also yielding quantitative products like kg, S of water, then adding transmitters, guidance, or intent, is multiplying entities for no gain. The real remains real without embroidery. The ore moves from mystery to mechanism. What about the but? It's interstellar instinct. That's precisely why this result matters. The water that wrote the 18 cm line didn't condense under our Sunday. It formed in another protoplanetary disk and slept in cold storage until our star woke it. The fact that the same OH physics held first heard cleanly from an interstellar comet tightens a bigger claim. Familiar chemistry travels. The surprise isn't that there's no beacon. It's that the cosmos keeps signing its name in the same ink, even when the paper comes from somewhere else. A final quality check. What would force us to revisit artificial? 3 things, at minimum. Non-thermal timing, a line that doesn't correlate with insolation or perihelion passage. Non-molecular frequency, a carrier off known transitions, especially near historically proposed universal bands, with follow-up persistence. Information-bearing structure, repeatable modulation, cadence that survives controls and retargeting. None appeared here. Instead, we recorded a clean instance of cometary OH, near 18 centimeters, peaking when it should, fading when it must, and shaped the way expanding gas is shaped. That isn't anticlimax. It's a standard, and standards are what let the next discovery move faster. For production going forward, the playbook is simple and testable. Book radio time bracketing perihelion for 18 cm OH, pair with optical IR, and define weird by deviations from the frequency timing shape triad above. If something breaks those correlations, you'll know it in the first hour of data reduction. Until then, physics wins, and that's exactly why this result will age well. Strip the romance, keep the record. The spectrum we logged checks every natural box. Where the line sits, how strong it got, the way it faded, and the shape it wore while doing it. Frequency. The feature landed exactly where hydroxyl must, near 18 centimeters, at the to 1665.402 and to 1667.359 megahertz's L doublet. Those are not chosen channels. They're fixed by quantum mechanics and used for comet studies precisely because they're reliable and repeatable. Strength versus distance. As solar heating climbed, the line rose. After perihelion, it decayed textbook behavior for thermally driven outgassing. That is what decades of OH monitoring show. Intensity tracks heliocentric distance because sublimation and photodissociation set the supply of OH in the beam. Decay rate. The post-perihelion fade matched a well-known arc production, drops with falling isolation, and the OH line slides back under the noise floor on schedule. Radio teams have used that rise and fall to time water production estimates since Halley and Hale-Bopp. It's how a transient becomes a measurement. Velocity distribution. The line width read like expanding gas, not like a beacon. A Doppler broadened profile consistent with coma outflow at sub-km, S to 1 km per second scales, with mild asymmetries that fit vents, jets, and rotation. That is exactly how OH line shapes have long been used to retrieve expansion speeds and diagnose coma physics. Put together, the 3 pillars, frequency, timing, shape, converge on nature. Fingerprint. O, at 18 centimeters, is the molecule's own signature, not an engineered carrier. Thermal clock. Intensity follows the sun, not us. Gas kinematics. Widths map to outflow velocity in the expanding coma. This is why the line is more than not noise. It's an audit trail. Integrate its area to count OH along the beam. Translate to H2O production with standard photochemistry. Compare widths to get expansion speeds. Then cross-check against optical morphology for a complete picture. That workflow is the backbone of comet radio studies, and it fits this dataset without adding extra assumptions. A note on confusion that often flares online. If you expect mystery, a clean match to OH can feel underwhelming. But in comet science, a spectrum that behaves this cleanly is the strongest possible result. It says the chemistry is doing what chemistry does in our system, and, crucially, beyond it. The same line that anchored Halley and Hartley's production rates now anchors an interstellar visitors, with the same tools and the same physics. So the montage is simple. 18 centimeters, right where OH must be, strength that obeys heliocentric distance, a decay curve that looks like every post-perihelion fade you've seen, a velocity spread you can read as expanding gas, no cadence, no modulation, no deviation from the molecular fingerprint, just a flawless natural signature. Begin with the plain fact. The water we detected did not form under our Sunday. The OH line at 18 centimeters only appears when water is present and exposed to sunlight. With 3I, Atlas, that means the molecules we heard were released from ice that condensed in another protoplanetary disk around another star long before Earth existed. What reached our antennas was not a message but the byproduct of ancient ice meeting new heat. Sublimation, photodissociation, and a photon at a frequency set by physics. How does water from another system end up in our sky? The pathway is familiar in broad strokes. In young disks, water condenses beyond the snowline, where temperatures are low enough for ices to remain stable. Dust grains rhymed with H2O aggregate into pebbles, pebbles into planetesimals, and some fraction of those are scattered by forming giants. A few are ejected entirely loose, cold archives carrying the chemistry of their birth environment. Most will wander interstellar space indefinitely. A small number, by chance, intersect our solar system and become what we label interstellar objects. Wandering does not erase identity. Interstellar space is harsh cosmic rays, UV, occasional grain-grain micro-impacts, but the top centimeters of a porous nucleus can absorb that processing, while interior ices remain effectively cryopreserved. Time engraves a weathered rind. It does not rewrite the core. When such a body finally crosses our inner system, the heating profile peels back that rind. Pores open, cracks propagate, trapped volatiles find pathways outward. The radio line we detect is the first audible consequence of that opening. Calling this cosmic archaeology isn't poetry. It's a description of method. Archaeology infers origin from residue and context. Here, residue is the molecular emission we measure. Context is the object's trajectory, the timing of outgassing, and the behavior of associated volatiles. We did not decode a transmission. We reconstructed a provenance. Water that formed under a different star is behaving under ours in a way that matches known comet physics. That continuity is the point. Physics does not localize to a single system. It travels. What specifically can we learn from a radio line about water that predates our planet? 1. Presence and process, not just appearance. Optical light shows that a coma exists. Radio confirms what is in it and how it's being supplied. The OH line demonstrates that H2O is actively being created and destroyed in sunlight now, not merely locked in dust grains. 2. Thermal coupling and structure. The way the line rises and falls with solar distance tells us how tightly the nucleus couples to isolation. A crisp perihelion peak and orderly fade imply that a significant fraction of the surface, or sunlit active areas, participates. Strong asymmetries can hint at vents or localized exposure. Either way, we're reading how ancient ice is architected in a porous matrix, then tested by a star it did not evolve under. 3. A comparative baseline across stars. Every OH radical, no matter its birthplace, emits at the same transition. That makes the 18 cm line a universal yardstick. When it behaves like textbook comet OH in our system, same frequency, similar widths, at comparable heliocentric distances, we gain evidence that the microphysics of cometary outgassing is not a local quirk. It's general. What this section is not claiming, we are not asserting a specific isotopic ratio like DH for 3I Atlas, nor are we declaring a measured CO or CO2 fraction here. Those require other bands and instruments. Our claim is deliberately narrower and safer. The radio detection proves that water ice native to another system was present and active. Its temporal and spectral behavior matched thermally driven outgassing when heated by our Sunday. Why does older than Earth matter beyond romance? Because stability under deep cold is a filter on formation environments. To carry abundant water for geologic timescales, a nucleus must have formed and remained in temperature regimes that never fully reset the ice. That points to a storage history in the outer reaches of its home system regions, analog to our Kuiper belt or Oort cloud source zones before ejection. The survival of easily destroyed volatiles through that history, tested in later sections with CO, 2CO and IR constraints, would further argue for very cold provenance. The OH line is the first doorway into that chain. No water, no doorway. There's also a calibration benefit. When an interstellar object reproduces the same line behavior seen in comets bound to our sun, it lets us compare like with like. We can ask concrete questions that move beyond adjectives. At similar heliocentric distances, do expansion speeds inferred from line widths cluster the same way as solar system comets? Does the activity ramp occur at about the same solar flux levels, or is there a systematic offset hinting at different surface porosity or thermal inertia? Do short-term deviations, small spikes, shoulders in the profile, align with optical outbursts, strengthening the case for vent opening, or crust failure over exotic drivers? Each affirmative cross-check narrows what we still need to know and prevents speculation from outpacing measurement. A common misunderstanding is that interstellar implies exotic. Sometimes it does, often it doesn't. Older than Earth means the material's origin predates our planet's formation, not that it violates known chemistry. In fact, the power of this detection is that it didn't violate it. Ancient water, new sunlight, expected line. The surprise isn't in the mechanism. It's in the reach how far from home the same mechanism still holds. From a production standpoint, this is what you emphasize in voice. The where of origin, another star's disk. The how of survival, deep cold preserving volatile inventory. The when of release, a brief window near perihelion. The what of evidence, a radio line at 18 centimeters that rises and falls with the Sunday. The why of meaning, a standard method now applied across stars hearing familiar chemistry in unfamiliar material. No mystique is needed. The awe is in restraint, a single narrow line converting a passerby into a dated artifact, a bit of deep time that only became legible when warmed. The comet did not speak, it obeyed, and in that obedience we found the continuity that lets science travel. The same molecule performing the same transition under a different sun, letting us weigh a breath that started its story before our oceans did. Start with what the eye swears it sees, a tail pointing toward the Sunday. It looks like propulsion, like thrust, but the scene is a trick of geometry, not intent. When our line of sight lies close to the comet's orbital plane, we look edge-on through a broad, flat sheet of dust that the nucleus has shed along its path. That dust sheet projects both ahead of and behind the nucleus, producing a spike that appears sunward, even though radiation pressure and the solar wind still push material away from the Sunday. 3I Atlas displayed this projection effect near perihelion in October 2025, with images showing a normal tail and a sunward-pointing anti-tail at the same time. The effect is optical and geometric, not dynamical. No special physics or propulsion is required. This isn't rare in principle, only in circumstances. Under the right viewing geometry, dozens of solar system comets have shown anti-tails. 3I Atlas simply gave us the alignment at a dramatic moment, so the sunward spike read as anomaly to casual viewers. The catalogued behavior remains the same. Dust sheet projection, not thrust. Now, add the brightness surges the flashes. Before and after perihelion, the light curve of 3I Atlas showed brief outbursts, sudden rises in brightness that then faded. That pattern is common in active comets and is typically tied to the physics of crust and ice rather than to guidance or transmissions. Thermal stress can fracture surface layers. A cliff face can fail. A crack can open to expose fresh ice. A small pocket of more volatile ices can vent. In each case, the immediate result is a short-lived increase in dust and gas production, which brightens the coma and tails before conditions settle back toward the isolation-driven trend. Observers documented exactly this sequence around perihelion for 3I Atlas, a rise keyed to solar heating, superimposed with short spikes that point to structural or compositional heterogeneity rather than anything engineered. Why do the surges feel unpredictable? Because the triggers are local and hidden from us. We cannot see the submeter architecture of the nucleus, only its integrated response. A small fracture propagating through a porous matrix doesn't run on a smooth solar distance clock. It runs on material failure, all or nothing, so the outburst timing deviates from a clean power law with heliocentric distance. That deviation fueled speculation online, but the standard comet explanation fits the facts with fewer assumptions. Heterogeneous nucleus, uneven venting, spikes from fresh ice exposure, then return to the thermal baseline. The available record on 3I Atlas says the same. Link the picture, radio and optical together. As solar heating peaked near perihelion, Meerkat recorded the 18 cm OH line water being liberated and photodissociated, while optical frames showed the coma tail system in full development, including the anti-tail from dust sheet projection. After perihelion, O8 intensity weakened as isolation fell, and the optical brightness faded overall, with a few short outbursts riding on that decline. Across bands, every trend tracks energy in, not Earth's attention. There's no cadence and no modulation. There are just physics and viewing geometry. A brief note about the two-tailed look that sometimes misleads. Comets carry both an ion tail, shaped by the solar winds, magnetic field, and a dust tail, shaped by radiation pressure. Filtered images often color these differently, but to the eye, they can overlap or cross. Add the anti-tail spike when we're edge-on to the dust sheet, and you can see three distinct structures from one object without invoking engines or steering. Observers reported exactly that composite morphology during the October-November window. Does rotation matter? Yes, and it helps explain the flash feeling. 3I Atlas's brightness variations suggest a tumbling state, a non-principal axis rotation that changes which vents face the sun and for how long. Tumbling, combined with heterogeneous ice distribution, creates asymmetric and time-variable jetting. That variability amplifies short-term changes in dust and gas output, exactly the kind of microweather you would expect on an active nucleus, and exactly the kind of thing that produces sudden brightening when a sun-facing region turns on. None of this requires artificial control. It requires a lumpy comet under changing illumination. What this section doesn't claim, we're not assigning a specific cause to each outburst. For example, cliff collapse at longitude X. We don't have that spatial resolution. We're also not calling every surge thermal stress. Some may reflect the venting of more volatile species. CO. 2. When a lid lifts. The conservative claim, supported by the record, is narrower. Short-lived, non-periodic brightening events are expected outcomes of structural heterogeneity and vent exposure on a heated, rotating nucleus. For 3I Atlas, the timing and character of the events match that expectation. Return to the anti-tail for the close. If you want a simple test for propulsion, ask what changes when we change where we stand. A rocket's exhaust vector should look like thrust from any angle. A dust sheet projection should be strongest when we're nearly in the orbital plane and should fade or disappear as our viewing angle shifts. The 3I Atlas anti-tail behaves like the projection, not like thrust. That it appeared alongside the ordinary anti-solar tails is precisely what geometry predicts and is documented across many comets under similar alignments. Rare in timing, routine in cause. So the montage resolves to one sentence. The strangeness is real, but the explanation is natural. Anti-tail? Projection through a dust sheet when we view the orbital plane edge-on. Flash? Short-lived outbursts from cracks, collapses, or fresh ice exposure riding on the solar distance curve. Both are signatures of an active comet near perihelion, made more striking here because the comet came from another star, and we happen to see it under rare, alignment-friendly conditions. The tools that explain similar scenes in our own system explain this one too, without adding intent. It moves fast. 14 to 17 kilometers per second sounds like intent. It isn't. It's bookkeeping. A body on a hyperbolic path around the sun carries more energy than a bound orbit allows. In orbital terms, its specific orbital energy is positive. Its conic is E is greater than 1. That alone tells you what you need to know. It is not captured. It will not return. It is passing through. Speed, in this context, is not a message, it's a receipt for where the energy came from and how gravity spent it. Two frames help keep the story clean. One, the sun's frame history, written as V infinity. Every hyperbola has a hyperbolic excess speed. Call it V infinity, the speed the object would still have far from the sun if you could turn the solar gravity off. That number reflects history, the object's ejection from its birth system, the relative motion of that system through the galaxy, and our own sun's movement. By the time 3I Atlas reached us, the sun had simply bent that inherited velocity around by a calculable angle. Gravity acted like a lens. It did not invent the beam. The Earth's frame perspective, not purpose. Speeds quoted near perihelion sound large because they are supplemented by the sun's pull. Any small body bound or unbound dives fastest near the Sunday. Long-period comets native to our Oort cloud routinely cross perihelion at tens of kms. Interstellar status does not grant 3i divided by Atlas, a special engine. It grants it no ticket home. The high number against the clock is normal for a close solar pass. So where does fast equals aiming creep in? Mostly from human instincts about arrows. We see a slender track crossing the inner system on a T-bone angle, and we project intention. Orbital mechanics doesn't. It cares about phase space, the set of positions and velocities that happen to intersect the slice of space we occupy when we happen to occupy it. A hyperbolic flyby through the planetary plane is not a targeting solution. It's an alignment that boosts detectability. If it had crossed 20 degrees above the ecliptic, most casual observers would never have noticed. The physics would be the same. There are 3 clean checks you can narrate that separate purpose from path. A. The curve follows gravity. Plot the orbit, and you get exactly the conic section two-body mechanics predicts, with small, well-behaved deviations from outgassing near perihelion. There are no course corrections, no discontinuities, no lateral impulses that would hint at thrust. The path is the sum of the sun's field plus tiny radially biased pushes from venting gas standard comet behavior, not steering. B. The energy budget closes without engines. Take the inbound V infinity, history, add solar gravitational focusing, subtract what little momentum the gas vents steal from the nucleus, and you recover the outbound V infinity, the before and after match. Nothing in the ledger requires extra power. The speed tells how, not who. A high perihelion speed is inevitable for any object diving to similar solar distances. Whether it started, bound eccentric to 1, or unbound, is greater than 1. What distinguishes interstellar is the sign, energy positive, not some exotic magnitude. In fact, many bound comets attain perihelion speeds as high or higher than interstellar visitors at similar radii. Motion repeats. Membership, bound versus unbound differs. Why then does it feel like guidance? Because selection effects amplify drama. We are far more likely to notice a visitor that crosses the ecliptic where we look most, b brightens near the sun where surveys are active, and sweeps past inner system landmarks we care about. That visibility bias reads as choreography. It's a coincidence filtered by attention. There's also the language trap. We say arrived quickly, and the brain hears arrived at us. But the destination in celestial mechanics is the perihelion point, a conic promise. Earth's vicinity is a spectator seat, not a bullseye. If Earth were elsewhere in its orbit, we would have watched a very similar hyperbola and told a much quieter story. A useful counterintuition. If 3i Atlas had guidance, you'd expect departures from the ordinary. A thrusting craft would resist the sun's plan, flattening the bend, holding altitude, changing the timing of closest approach. We saw none of that. We saw the plan gravity writes for everything small, with the mild, sun-facing nudge common to outgassing comets. In a spectrum, you'd expect modulation or timing artifacts tied to control. We saw a natural OH line tied to heat. In images, you'd expect exhaust that doesn't care about geometry. We saw tails that do ion tail anti-solar, dust tail along track, anti-tail appearing only when viewing angle aligned. History, not intention, explains the inbound speed. Picture a young planetary system ejecting debris as giant planets migrate. A small body gets flung onto an escape path at a few km/s relative to its star. Stars drift through the galaxy at tens of km/s relative to one another. Some vectors wait for millions of years, and a fraction of those ejected bodies will pass through the sun's sphere of influence. Most will miss the inner system entirely. A few will cut the planetary plane when we happen to be watching. Those few are overrepresented in our stories. They are not overrepresented in nature. Even details that sound aimed like a low inclination, pass close to the ecliptic, are probability funnels, not steering. The ecliptic is where our survey coverage, dust sheet projection effects, and brightness cues all improve at once. Objects skimming that plane are easier to detect and easier to watch. That doesn't make them chosen. It makes them visible. For voice, you can pin the logic in 4 short beats. Hyperbola equals unbound. Positive orbital energy, no return ticket. Perihelion speed is normal. Close to the sun, everything dives fast. No thrust signatures, trajectory smooth, spectrum natural, tails obey geometry. Alignment is not equal to aim. We saw it because the angle helped, not because we were the goal. There is a dignity to this restraint. We don't need guidance to make the scene meaningful. The meaning is that an object formed under another sun acquired a velocity long ago, kept it, and let the sun curve it once when it crossed our neighborhood. We learned from the bend, weighed its breadth at closest approach, and watched it leave with the same energy it carried in. Speed, in that light, is not a shout across space. It is a memory, a conserved quantity carried for ages, briefly audible when gravity and sunlight make it legible. We did not intercept the intention. We intersected motion. Pointing backward is easier than pointing home. From our brief window around perihelion, we solve an orbit and extend it outward, propagate the hyperbola into the past, and the track pierces the sky near Draco. That's a direction, not a birthplace. It says, the object came from there recently, not it formed there. Between those two statements lies the part of space most people never picture. The galaxy as a slow river with layered currents, eddies, shear, and drift. Start with a scale that fits in your head. A handy rule: 1 kilometer per second is approximately equal to 1 parsec per million years. If a fragment cruises through the Milky Way at 20 kilometers per second, different from the local stellar flow, it displaces roughly 20 parsecs every million years. In 10 million years, that's 200 pc, hundreds of light years. Over the longer spans likely for an ejected body, the original neighborhood is gone, its stars spread along the spiral arm like chalk rubbed across a sleeve. A constellation in our sky is a pattern, not a place. Over time, patterns unweave. The galaxy adds structure to that drift. The sun orbits the center roughly every few hundred million years. Superposed on that, stars execute small epicyclic loops, lateral oscillations from the disk's differential rotation. They also bob up and down through the mid-plane. Giant molecular clouds pass like slow freight trains of mass, and each encounter tweaks velocities. None of these nudges is dramatic. Taken together across eons, they scramble provenance. Even if 3I Atlas left its home on a clean outbound lane, galactic traffic has been adjusting its speedometer needle ever since. Now add our own uncertainties. We don't observe the nucleus directly for long. We observe the coma that hides it, and we fit an orbit from a short arc when it's brightest and perturbed. During the weeks around perihelion, sunlight drives non-gravitational acceleration, tiny sun-facing pushes from gas jets. Those pushes slightly alter the path we try to extrapolate backward. We correct for them, but every correction has error bars, and error bars multiply when you run the clock in reverse. That's why somewhere near Draco is the right level of confidence. It's a cone in the sky, widening with every million years you rewind. Inside that cone live thousands of stars at a mix of distances. Which one, if any, helped eject this object? To answer that, you need 3 things at once. 1. A well-constrained past trajectory for the object, with non-gravitational terms modeled. 2. Precise 6-dimensional phase space data, positions and velocities for surrounding stars. And 3. A galactic potential to integrate everything. We possess versions of all 3, but the time baseline and the tiny perturbations defeat certainty long before you reach a plausible ejection epoch. You can hear the limits in the language astronomers use: backtracing, candidate encounters, consistency. For other interstellar visitors, groups have run the film backward and flagged close passes with known stars, brushes that could be places of origin, could matters. A near pass is not proof of launch. It's an invitation to check timelines, stellar ages, and planet architectures. Most candidates fade under scrutiny. The object's momentum remembers a direction far better than it remembers a cause. Think about the ejection itself. In young systems, giant planets migrate, resonances pump up eccentricities. Small bodies are handed from one gravity well to another until one of 2 things happens. They crash, or they clear escape velocity. That last kick is surgical and indifferent. It doesn't stamp a return address into the ice. It imparts a small deltav, sets a sign on the energy, and the fragment joins the broad interstellar traffic. From that moment, origin is a statistical concept, not a stamp on the hull. Even if we could rewind perfectly, The birthplace might not be there to find. Star-forming regions dissolve. Associations disperse. A cluster that ejected a cometary shard can shear apart into a loose spray of field stars. The parent star might have migrated radially within the disk. It might have changed neighbors entirely. Our best telescopes can label sibling stars that likely formed together by matching chemical fingerprints and dynamics. But a lone ice rock, processed by radiation and resurfacing, carries no such chemical tag we can read at solar system distances. We hear its water, we don't see its natal cloud. There is one thing the direction can test: recency. If the inbound vector points near a known moving group and the object's speed relative to that group is small, the ejection could be geologically recent a few million years, because the traffic hasn't had time to stir. If the vector and every nearby group disagree, the travel time grows, and the origin search dilutes across kiloparsecs. With 3I, Atlas, the best you can say with integrity is conservative. The approach direction is consistent with a long, home-detached cruise, not with any single, compelling, recent launch site we can name. So why cite Draco at all? Because the sky needs a handle, and a rough inbound cone helps coordinate observations, models, and public understanding. It tells survey teams where to look for the next objects arriving from similar galactic longitudes that might be more common, given the sun's current motion through the local flow. It also reminds us that selection effects matter. Visitors arriving near the ecliptic plane are easier to detect, so our early catalogue will be biased toward convenient alignments, not representative. There is a humbler question underneath the haunting one. Not where did it come from, but what can a direction, plus a spectrum, plus a light curve, already answer? Quite a lot, from direction, unbound, and roughly how the sun bent it. From spectrum, water present, O8 at 18 centimeters, production rates, and expansion speeds. From the light curve and morphology, active nucleus, anti-tail by geometry, outbursts by structure. Most of what matters for physics, what it is and how it behaves under our star, we know without a return address. If you need one line for voice that keeps curiosity honest, use this: motion preserves momentum better than it preserves memory. Momentum brought 3I, Atlas here. Sunlight made it legible, gravity curved it on schedule, and then momentum will take it out again, with almost exactly the energy it carried in. We can label the last few astronomical months in detail. We can sketch the last few million years as a vector through a moving crowd. Beyond that, the galaxy washes origin into probability. None of this makes the search small. It makes it repeatable. Each new interstellar object adds one vector and one set of materials to the map. Patterns will emerge where single cases could not. Preferred approach longitudes, volatile mixes that cluster by broad galactic environment, rotation states that hint at shared collisional histories. In that ensemble, direction with no destination becomes a dataset with structure, and structure is how science replaces ghosts with maps. For now, the honest ending is this: near Draco is where the trail in the sky points, not where the story began. The home this object left may be dispersed, migrated, or simply unrecognizable in the frame we can reconstruct. What we can fix, we have: a clean hyperbola, an OH line that rose and faded with heat, and a short, vivid chapter in which ancient ice met our sun and told us in the only language it keeps the kind of traveler it is. Begin with the measurement, not the myth. Spectra taken as 3I. Atlas approached perihelion, resolved strong volatile lines, water, carbon monoxide, and strikingly carbon dioxide in a proportion higher than is typical for many solar system comets observed at comparable solar distances. That ratio is the clue. CO2 is more volatile than H2O. It lifts at lower temperatures and farther from the sunday. Seeing CO2 so clearly means the nucleus carried a reservoir that survived storage in deep cold for a very long time, then released it when sunlight crossed the activation threshold. Volatility is a thermometer. In comet science, which species switch on, and when maps directly to thermal history, water waits for heat, carbon dioxide does not. If an object retains substantial CO2 after a multi-million-year cruise between stars, the implication is conservative and powerful. The bulk stayed cold enough that CO2 never had the long, slow bake needed to diffuse out. That is exactly the inference drawn for 3I. Atlas, high CO2, alongside robust water activity, indicating a nucleus preserved at cryogenic temperatures until solar heating woke layered volatiles in sequence, place the radio detection back into the picture. Meerkat's 18cm hydroxyl line caught water's downstream chemistry. H2O sublimates, then UV breaks it, and OH radiates at a narrow diagnostic frequency. Because OH intensity scales with water production through known photodissociation physics, the radio curve becomes a quantitative gauge of H2O output, independent of dust assumptions. Around late October 2025 near perihelion, the OH line rose and then weakened with falling isolation, tracking the expected energy in, response out pattern. That told us when water dominated. The spectra told us CO2 was there early and strongly too. Together, they fix a timeline. CO2 active at larger heliocentric distances, H2O peaking near perihelion, both consistent with a cold-stored, volatile-rich nucleus. What does older, colder mean in practice? It doesn't claim an exact age. It claims a custody chain. In young planetary systems, ices condense at temperatures set by distance from the local star and disk conditions. Bodies that form farther out trap more CO2 and other volatiles. If later ejected into interstellar space, a subset will spend geologic time at a few tens of Kelvin, protected from repeated perihelion cook-offs that deplete CO2 in many short-period comets. When such a traveler finally encounters a new star, its first voice can be CO2, then H2O, precisely the order implied for 3I, Atlas by the combined radio, optical record. The uploaded analysis distills this. The relatively high CO2 content suggests it has been cold enough throughout its journey to preserve these volatile ices, leaving us a less processed sample of its birth environment. This is why the ratio matters more than the headline. In our system, CO2 is common, but the CO2-H2O balance varies with formation zone and thermal processing. For 3I, Atlas, the observed balance trends higher than typical, which is exactly the sort of comparative signal you want from an interstellar specimen. Not alien in physics, but informative about conditions there. It points to colder disk chemistry or a formation radius farther from its natal star than is usual for many comets we repeatedly reheat here. The uploaded text makes that point directly. A higher CO2-H2O ratio is consistent with formation in colder regions and long-term preservation. Caution belongs in the same breath. Our sample of interstellar comets is still tiny. Higher than typical is a comparison to solar system populations with their own biases. The correct scientific posture is to treat 3I, Atlas, as a well-constrained data point, not a template. The analysis file notes this explicitly. Small number statistics limit claims about what's usual for other systems. The high CO2 is a clue, not a verdict. It becomes powerful when added to a growing ensemble over the coming years. Link ratio to structure. A nucleus that retains CO2 after eons is probably heterogeneous and porous, with volatile pockets and crusts that fracture under thermal stress. That gives you the outbursts, short-lived surges riding on the broader solar distance trend as fresh ice becomes briefly exposed. The uploaded record ties those spikes to structural heterogeneity and vent exposure, not exotic engines, and places them right where you'd expect. Near and just after perihelion, when the thermal gradient bites deepest, CO2's presence at depth helps explain why a small crack can produce a large, sudden brightening. An insulated pocket suddenly finds space. What about mass and survivability? The radio-inferred H2O production rate, combined with optical coma behavior, points to a nucleus on the order of kilometers across, enough inventory to sustain significant activity and still leave with much of its volatile budget intact. The analysis emphasizes this as well. A several-kilometer nucleus can carry substantial ice and preserve it over immense timescales, exactly the kind of reservoir that can hold CO2 until a warm passage. There is also a comparative lesson folded inside the 18cm line. The OH spectrum from 3I Atlas looks normal line shape, expansion speeds, and temporal evolution match expectations for a comet at that solar distance. That normalcy matters. It tells us that while the origin is interstellar and the CO2 reservoir is generous, the physics of release and expansion honor the same rules we've calibrated on hundreds of comets here. Same chemistry, different sun. So the narrative of CO2 becomes a disciplined arc. Observation: strong CO2 alongside water and other volatiles, with CO2, H2O, trending high relative to many solar system cases. Physics: CO2s, lower sublimation temperature, makes it a tracer of cold formation and storage. Its survival signals long-term cryogenic custody. Timeline: CO2 can turn on earlier. H2O peaks near perihelion. O radio intensity follows isolation, quantifying water release. Structure: heterogeneity explains outbursts. Cracks expose fresh ice. Spikes ride the solar curve. Inference: colder birth environment and pristine preservation give a cleaner sample of alien disk chemistry without invoking anything non-natural. One last perspective: why this matters beyond a single visitor. With 3 interstellar objects now on the books and radio, optical workflows proving their worth, each additional visitor will let us map CO, 2H, 2O, and other key ratios against approach geometry and solar distance. Over time, that will turn a single cold-preserved story into a distribution, which is how comparative planetology graduates from anecdotes to constraints. The uploaded file sketches that broader shift too. We're moving from lone events to a population study, where ratios like CO2, H2O become the axes of a new diagram for other suns. In the end, older and colder are not flourishes. They are conclusions you can narrate with numbers. The high CO2 content is consistent with cold formation and long preservation. The OH line quantified water release on schedule. The light curve and outbursts fit a heterogeneous, volatile-rich nucleus under stress. The traveler didn't send us a message. It brought us a thermometer, and it still reads low. Put them on one table and read the contrasts. Oumuamua, 2017. An object without a visible coma, bright but dust-poor, tumbling with a light curve so extreme it looked like a shard. It showed a small, persistent, non-gravitational acceleration without the usual signatures of outgassing in reflected light. No 18 cm line was caught. By the time the world looked up, it was already leaving. It taught us how blind we were to fast, faint interstellar passers-by, and how a single anomaly can dominate the headlines for years. 2I, Borisov, 2019. The Mystery Antidote. A textbook comet from another star. A sprawling coma, dust and ion tails, steady outgassing, colors and spectra that felt comfortingly familiar. If Oumuamua said interstellar can be strange, Borisov said interstellar can be ordinary. Together, they widened the category. Visitors need not choose between uncanny and normal, they can be either. 3I, Atlas, 2025. The most instrumented so far. Optical images showed a lively coma with geometry-driven features, the occasional sunward antitail when we viewed the dust sheet edge-on, plus brief outbursts near perihelion as cracks exposed fresh ice. Radio teams heard it at 18 centimeters, the hydroxyl line that appears when water sublimates and sunlight breaks H2O apart. Later analyses flagged an unusually high CO2, H2O balance, compared with many solar system comets at similar distances, evidence for long cold storage before our sun woke it. Nothing about that ledger requires design. Everything about it rewards measurement. Lay those 3 columns side by side, and the pattern is plain. Diversity is the rule. One object without a visible coma, one entirely comet-like, one comet-like with rare geometry and a strong CO2 presence. The interstellar population is not a single species. It's a spectrum of histories, sizes, and surface states. Natural mechanisms survive the trip. When outgassing is present, it behaves as physics says it should. At 18 centimeters near peak heating, line widths set by expansion speeds, tails that obey solar wind and radiation pressure, antitails explained by projection. When outgassing is weak or absent, dynamics can still show tiny non-gravitational nudges that don't need engines to exist. Low-level sublimation can do the pushing, even when dust is scarce. Origin is elsewhere, not other. The chemistry that breathes under our sun breathes under theirs. Water writes the same radio line. Dust scatters light the same way. What changes is proportion and timing, the mix each body carried out of its own disk, and the order in which sunlight awakens it. The real revelation isn't that one of them signaled. It's that we're starting to catch them at all, and to catch them with the right tools. Pan-STARRS and Atlas made the first two discoveries possible. Coordinated optical campaigns, plus Meerkat and other arrays, turned 3i Atlas into a multi-band case study. The next step is not a leap of faith. It's an upgrade of coverage. Rubin scanning deeper, Neo Surveyor adding thermal eyes, radio arrays booking time around perihelion by default. As those instruments come online, the gap between we noticed and we measured will shrink. The fear that rare equals special is giving way to the math that rare equals undersampled. Once you look wide and often enough, wanderers show. Some will be dusty, some austere, some fractured and loud. A few will streak through inconvenient geometries and leave only questions. Many will arrive where we can weigh their breath and watch their structure fail and recover in the light. Each adds one dot to a scatter plot of volatile ratios, rotation states, line widths, and activity timelines. Dots become clusters. Clusters become a map. The silent promise inside these three visitors is practical. We can prepare. We can define weird, not by vibes, but by deviations from a growing library frequency, timing, and shape for radio lines, morphology and color for optics. CO, CO2, H2O for IR. When a true outlier arrives, we'll know in the first 24 hours which column it belongs to, and whether the story is another flavor of natural or something that broke the template. Three visitors don't complete a pattern, they start one. And the pattern they sketch so far says this: interstellar objects are diverse, detectable, and decipherable. The miracle isn't intention. It's access that we now have the ears and eyes to turn a fast hello into numbers that travel. Keep it simple. The ingredients are familiar. The mix is new. With 3i Atlas S, we measured water by its downstream OH at 18 centimeters and watched that line rise near perihelion and fade after exactly how cometary water behaves when sunlight cracks H2O and populates the OH IL doublet at 1,665, 1,667 megahertzes. That's not a preference. It's a quantum rule we've used on comets for decades. Same transition, same physics this time, in material that formed under another star. Different shows up in the ratios and in timing. Radio and optical work put water on the clock. Complementary spectra flagged CO2 as unusually strong compared with many solar system comets at similar distances, because CO2 sublimates colder and earlier than H2O. A high CO2-H2O balance points to long-term cryogenic storage before our sun warmed the surface. That's a different proportion, not a different law. We have precedent for same chemistry, new mix. 2i. Borisov, also interstellar, carried exceptionally high CO. Unlike most short-period comets we reheat repeatedly, ALMA's measurements set it apart compositionally while keeping it squarely natural in behavior. Chemistry varies with formation radius and processing history. The rules don't. Even Oumuamua, the outlier with no visible coma, underscored this lesson after the headlines cooled. Its small, non-gravitational push fits ordinary forces outgassing at unusual scales or radiation pressure without needing new physics or intent. Three visitors, three personalities, all remain explainable inside the same mechanics and chemistry we test at home. Zoom out to where such mixtures are made. Protoplanetary disks around other stars show water, CO, and CO2 in arrangements that depend on temperature, UV field, and dust evolution, exactly the knobs we expect from theory and now probe with JWST and ALMA. The inventory changes with the environment. The playbook volatility, photochemistry, transport, does not. Occasionally, disks look surprising CO2, rich zones with weak water vapor, or chemistry shaped by harsh UV near massive stars. Those cases don't negate universality. They map its parameter space. Change the lighting, and you change the mixture. The equations stay put. That's the pivot this section delivers without mystique. Universality is not equal to uniformity. 3i. Atlas breathes the same molecules our comets breathe. It lights the same OH line our receivers expect. It builds a coma, throws dust and ions into tails set by sunlight and the solar wind, and under edge-on geometry draws a sunward anti-tail from a dust sheet. Familiar behaviors, different proportions, foreign origin. Why this matters for life's chemistry is pragmatic, not speculative. If multiple disks routinely assemble and preserve water-bearing solids, and if those solids can be ejected and still arrive with intact volatiles, then the conditions that feed habitability are not parochial. We're watching transport and preservation mechanisms that many systems share. We're not invoking intention, just inventory and logistics. The universality we can measure is that the same physical pathways recur under other suns. So the sentence to carry forward is this: same laws, different stars. The line at 18 centimeters didn't become special because it came from elsewhere. It became useful because it didn't change. That stability lets us compare CO2H2O against solar distance, line widths against expansion speeds, outburst timing against thermal stress, and turn a one-off encounter into a point on a growing, cross-stellar diagram. The surprise isn't that we recognize the chemistry. It's that we can now hear it in time to weigh it. It wasn't luck. It was a plan. A fast, faint visitor was inbound. Optical teams would see the coma and tails. But to weigh the water, you need to hear the molecule that sunlight makes. That set the target for radio. The hydroxyl OH main lines near 18 centimeters to 1,665.402 and 1,667.359 megahertzes. Meerkat 64 13.5-meter dishes spread across the Karoo had the sensitivity, the bandwidth, and the radio-quiet sky to go after them. Point, track, calibrate, integrate, then let the chemistry speak. Why is 18 centimeters the right ear? When solar UV splits H2O in a comet's coma, OH is produced. Those radicals are pumped by sunlight and de-excite by emitting at the two narrow main lines around 1,665 and 1,667 megahertzes. Detecting those lines does three things at once. 1. It confirms water unambiguously. 2. It turns the line area into an estimate of OH column density. And, via standard photochemistry, H2O production rate. 3. The line width. Shape reveals the speed and symmetry of gas flowing off the nucleus. No bright image required. Radio can work even when the comet is a visual whisper. How Meerkat makes a big ear out of many small ones. Interferometry knits dozens of dishes into a synthetic aperture. In practice, that means exquisite sensitivity, plus the spectral resolution to resolve a line only a few kilohertz wide, a few hundred ems, km, s, in velocity space. A typical observing sequence for a moving target like 3I Atlas looks like this in plain voice. Doppler tracking. You compute the comet's topocentric velocity so the OH lines land in the correct channels. Bandpass, flux, phase calibration. Point briefly at known calibrators to flatten the instrument's response and lock amplitudes and phases. On-off strategy. Alternate the comet with a nearby blank field to model and subtract the residual background. RFI hygiene. Flag terrestrial radio noise, then reintegrate the clean channels. Stack and align. Co-add the time slices in the comet's rest frame so any faint line grows while random noise averages down. Do that around perihelion when solar heating is strongest, and the OH line should rise out of the continuum if water is flowing. That is exactly the window Meerkat was scheduled for. Without needing light, optical seeing can be poor, moonlight can be unhelpful. A low albedo coma can be underwhelming visually even when gas is abundant. Radio is indifferent to glare and darkness. With 3I, Atlas, the line emerged on schedule. 18 centimeters, right where OH must be. Strength consistent with an active coma at peak heating. A profile broadened by outflow. Even if the pictures had been mediocre, the molecule would still have left its signature on the dial. What the spectrum gave the team, a number for water, integrating the line delivered kg S of H2O, independent of dust assumptions, a speed for breath. The full width is mapped to expansion velocity gas, racing off the nucleus at hundreds of meters per second up to 1 kilometer per second scales. At that distance from the Sunday, a test of timing. the rise near perihelion, and the fade after locking the driver to isolation, not to Earth's position or any transmitter-like cadence. The beauty in the method: optics and radio told the same story from different angles. Optical frames showed a normal ion tail, a dust tail, and when our view lined up edge-on with the dust sheet, an apparent anti-tail spiking sunward. Radio, meanwhile, weighed the gas feeding all of that and proved it was waterborne. 2 bands, 1 physics. Why MeerKAT mattered specifically. The Kourous protected spectrum lets you actually use the 18 cm band. The array's collecting area and back-end can watch narrow cometry lines while also being agile enough to follow a moving, accelerating source. And because it's an array, you can form tide array beams or small images to verify you're on target, then pour everything into spectral integration. The result: sensitivity high enough to make an interstellar comet's OH line a practical target within a short perihelion window. Calling this the first successful radio capture from an interstellar comet isn't a flourish, it's a milestone. It sets a playbook other facilities can follow. 1. Trigger radio time as soon as surveys flag an interstellar inbound. 2. Bracket perihelion to catch rise and decay. 3. Doppler track and stack in the comet's frame. 4. Publish H2O production rates and expansion speeds alongside optical IR results. 5. Archive spectra so future visitors can compare line for line. What's next? Rubin will find more of these wanderers earlier. Neo Surveyor will add thermal context. SKAMID will extend MeerKAT's approach with even greater sensitivity, making 18 cm OH routine for faint comets and pushing to weaker lines and more distant geometry. And Coordinated Campaigns will add CO and CO2 from IR instruments, giving a full volatile ledger. Who turns on first? Who dominates? Who lingers? The quiet triumph here isn't that we heard a message. It's that we taught our instruments to listen to molecules and they answered. A narrow line, a measured width, a timed rise and fall. That's enough to turn a passing speck into a physical story. MeerKAT proved the workflow works on an object from another star. The next one won't be an experiment, it will be a procedure. We didn't get lucky. We built a lane. 3. iAtlas taught us the sequence. See it early, solve it fast, listen on time, compare across bands, and archive like a lab notebook. The next visitor won't be a scramble. It will be a procedure. Start at the top of the funnel discovery. Wide field surveys sweep the sky every night, subtracting last night's image from tonight's to find what moved or changed. Trailing loss used to hide fast movers. Now streak-finding algorithms flag even thin, diagonal smears as candidates. Brokers push alerts in minutes. The moment a tracklet shows non-sidereal motion that doesn't fit the catalogue, the orbit solvers get to work. Fit a preliminary arc. If the energy looks positive, unbound. Raise the flag. Interstellar candidate. Don't chase everything. Chase what you can measure. Early arc quality sets the whole campaign. Phase 2. Pin the path. Cue rapid astrometry from multiple longitudes to lengthen the arc and collapse uncertainties. Publish to the clearinghouse so anyone with a telescope can help. Fold in Precovery, dig through recent images to find the same object a few nights earlier and the orbit tightens again. Within a day, you know if it's hyperbolic. Within 2, you know the perihelion date and the distance window where volatile lines should sing. Phase 3. Book the ears. This was the 3I Atlas inflection point. Optical images are wonderful. Radio turns pictures into rates. As soon as the object is a serious interstellar object, request bracketing time around perihelion at arrays that can resolve the 18 cm OH lines. Set the plan now, not later. Doppler track in the comet frame. Alternate on-off fields. Stack by the object's velocity. Keep RFI out. Integrate long enough to pull a narrow line out of a noisy continuum. That turns a visit into a water ledger. Kilograms per second at specific times, with line widths that read expansion speeds. In parallel, infrared adds the missing thermometers CO and CO2, so you can chart who turns on first and how the balance shifts with distance. Optical photometry and imaging map the coma and tails, log outbursts, and catch the anti-tail if the geometry lines up. 3 bands, 1 story. What's there, how fast it leaves, and how the structure answers the Sunday. The checklist is the revelation, not the signal. The order we execute it. What changes with the next one is capacity. Vera Rubin Observatory will do discovery at scale, night after night, with deeper limiting magnitudes and faster cadence. That means earlier detections, more days on the clock before perihelion, and cleaner orbits from the start. NEO Surveyor will add thermal eyes from space, catching dark, cold travelers that optical surveys miss and telling us sizes without guessing albedo. Meerkat has proven the OH workflow. SKA-MID will push it fainter and farther, turning 18 cm comet lines into routine time domain radio. The same playbook scales. Listen earlier, hear more. Phase 4. Make weird a category, not a feeling. From 3i, Atlas, we learn the triad that keeps us honest. Frequency. Is there power on a known molecular line? For example, O at to 1,665, 1,667 megahertzes, or off it. Timing. Does intensity track heliocentric distance isolation, or something independent? Shape. Does the line profile read like expanding gas, or does it carry modulation? Cadence. Natural passes when the triad aligns. Investigate when one leg breaks. We can publish that rule of thumb on day 1, so amateurs and pros are speaking the same language when the speculation starts. Phase 5. Schedule like a mission. No more hope the weather cooperates. Assign roles. A coordinator keeps the master plan. Radio leads own OH windows. IR teams own CO, CO2. Optical teams own morphology and light curves. A small timing cell watches for rotation and outburst cadence. A data steward runs the archive, where spectra, images, and calibrations land with timestamps, ephemerides, and reduction notes. If the object is bright enough, spin up public dashboards so everyone sees the same curves in near real time. The instrument isn't the dish or the mirror. The instrument is the network people, schedules, and a shared clock. The standard also includes edge cases. If the inbound object is unusually faint or fast, use streak stacking at survey cadence. If perihelion falls behind the sun from Earth's point of view, lean on spacecraft and heliophysics images that can see closer to the glare. If the weather kills a key night, the plan already has an alternate site pointed at the same line and the same calibrator stars. Redundancy is the difference between a souvenir and a dataset. For voice, show how the new era feels different. Before, find Marvel, miss the window. Present, in find A. Now, find, solve, schedule, listen, compare, publish. The quiet miracle is that none of this requires a perfect object. It requires discipline. With 3i, Atlas, we caught an interstellar comet at the right hour and turned its pass into numbers with units. Megahertz, M, S, kg, S. The next one may be dust poor or oddly inclined. The triad still holds. If the OH line rises with isolation, if the profile reads like gas, if the frequency sits on a transition nature already used, we have our baseline. Deviations, true ones, will shout through that baseline without us straining to hear them. What about public conversation? Bake the comparison into the first statement. Here is the plan. Here are the 3 checks. Here is today's update. When the anti-tail appears, we explain the geometry as we show it. When an outburst spikes, we mark it on the light curve and line up the radio to see if water followed. When the line fades after perihelion, we call it what it is. The sun dimming in the object's sky, and the comet answering with less breath. The question isn't, is another coming? The question is, are we already booked for its window? By the time Rubin is scanning nightly and SKA-MID is live, this will feel like weather. Events to cover, not marvels to miss. Well, chart approach directions against the sun's motion, and learn whether certain longitudes are richer in wanderers. Well, collect volatile ratios into a plot that finally has more than a handful of points. Well, stop treating interstellar as a synonym for exotic and start treating it as a population with trends, outliers, and rules we can test. A standard once written does something subtle to awe. It moves it from the headline into the work. The thrill isn't that a line appeared at 18 centimeters. It's that everyone knew where to aim and when to listen. And the line arrived on schedule. That's not routine. That's mastery earned by the last object, so we don't lose the next. The era has already turned, The sky will keep sending wanderers. Our choice is whether they pass as rumors or whether we catch them with a method that outlives our surprise. Humility is part of the instrument. We measured a clean OH line at 18 centimeters. We traced a hyperbola. We watched a coma build, tails separate, an antitail appear under edge-on geometry, and short outbursts ride the solar distance curve. And yet, the ledger of unknowns is longer than the memo of facts. That isn't failure. It's the shape of honest progress. Start with the loudest blank, origin. Inbound from near Draco is a direction, not a birthplace. Backtracing through a moving galaxy, with small non-gravitational pushes near perihelion and uncertainties that widen with every million years run in reverse, leaves us with a cone, not a street address. The star that formed the ice may have migrated. Its birth cluster may have dispersed. The ejection kick that set this body free left no tag we can read at telescopic range. We know where it was. We do not know where it began. Age is another open door. Older than Earth is safe only in the broadest sense. The ices formed before our oceans, then slept cold for a long time. But how long? 10 million years? 100? More? Without a laboratory sample or a specific isotopic clock from high-resolution spectroscopy we don't yet possess for an interstellar visitor, the number stays qualitative. Time here is a range, not a date. Even size and mass live behind hedges. Water production rates from the OH line, plus coma behavior in optical light, suggest a nucleus on the order of kilometers. But dust-to-gas ratios vary. Albedo hides truth, and shape matters. A compact, dark body and a larger, brighter one can throw similar visual signals for different inventories. We can bracket, not pin. Beneath the coma lies a structure we can only infer. Porosity, crack networks, tensile strength of crust, layering of volatiles. These are the details that govern outbursts and set the cadence of activity. The evidence we have points to heterogeneity. Vents switching on and off, fresh ice being exposed, thermal stress opening seams. But the architecture driving those events is submeter, hidden under kilometers of integrated effect. We model, we do not see. Even something as basic as rotation is only sketched. Light curve irregularities and jet asymmetries hint at a tumbling, non-principal axis state. If so, which periods? How stable are they? Does the torque from outgassing reorient the body across weeks? We have clues, not a solved spin state. And without a nailed rotation, separating rotational modulation from intrinsic outbursts in the light curve remains a controlled guess. We also do not have a full chemical ledger. Radio told us water was present and let us weigh its release. Complementary spectra argue for a relatively high CO2H2O balance. But what of CO in detail? Organics? Refractory composition? Grain size distributions? Polarimetry teased at dust properties, yet translating scattering behavior into unique mineralogies is notoriously non-unique. The same is true for temperature fields. Thermal inertia controls how deeply heat penetrates and how long vents persist after sunset on the nucleus. But we read that parameter obliquely, through timing and rate, not directly. There is no precise D, H for the water, the isotope ratio that, in solar system comets, anchors debates about the origin of Earth's oceans. For an interstellar object, a D, H, would be a Rosetta Stone for disk temperature history. For now, it stays blank. The same goes for noble gases and other sensitive tracers. Our instruments weren't positioned, or perhaps not yet built, to pull those threads this time. Our dynamics are almost right, which is different from right. Non-gravitational acceleration near perihelion, the gentle, sun-facing push from gas escape, has to be modeled to refine the orbit. We can fit it with standard parameters and get a consistent path. But every non-gravitational term carries covariance with the fitted geometry and rotation, and that covariance grows when we extrapolate to the deep past. We're confident about unbound. We're less confident about from exactly here, exactly then. We don't know the fragmentation risk beyond the observational fact that it did not catastrophically break while we were watching. Did it shed small pieces we missed? Do those fragments seed a transient meteoroid trail that will intersect anything we care about? With a single apparition, limited baselines, and strong selection effects near perihelion, we cannot say. The safest statement is local, The light curve's behavior and tail morphology were consistent with outbursts and modest shedding, not wholesale failure. Consistent with is not ruled out. We don't know whether its core remains pristine. Activity processes surfaces. Even a first warm pass around our sun can rework mantles, plug vents with sintered dust, alter porosity, and lay down a dehydration crust. If the body saw earlier warm episodes near its home star before ejection, that history is written in layers we cannot peel at a distance. We met it one chapter late and had to infer the prologue. We don't know if we heard everything. O is loud and diagnostic. That's why we targeted it. But weak lines from other species could be present below our sensitivity, telling subtler stories about oxidation state, radiation processing, or parent molecule inventories. Meerkat did what it was built to do, and it did it well. The unanswered part is an engineering challenge for the next campaigns. Wider bandpasses, deeper integrations, better RFI shielding, and tighter scheduling around perihelion. We don't know the outlier space yet. With 3 interstellar objects on the books, normal is a moving average with error bars as big as the plot. Does high CO2 H2O mark a common interstellar trait or a tail of the distribution? Are non-principal axis spins typical of ejected rubble, or did we just happen to catch one mid-tumble? Do anti-tails appear more often for interstellar objects because their inbound geometries bias us toward favorable plane crossings, or is that simply a coincidence of this year's sky? Each question is answerable in the plural only with population, not with a single case. We don't know the right places to look yet. Rubin will help answer approach longitude biases. Neo Surveyor will reveal size distributions we presently misjudge because albedo plays tricks. SKA Mid will pull OH from fainter comets farther from perihelion, mapping the rise earlier and the fade later. Until those pieces come online together, our strategy has seams and our maps have holes we can already see. And finally, we don't know how much ore we'll have to recalibrate. The risk in clean, natural explanations is complacency, mistaking mechanism for monotony. The corrective is simple and stern. Write the standard, publish it, and then dare the data to break it. Mystery is not the absence of answers. It is the space we defend for surprise by refusing to overclaim. Every we don't know above is not a shrug. It's a to-do list. Keep the motifs honest. Light set the clock. Breath made the line. Memory rode in the conserved momentum. Silence was the absence of modulation. Everything else, origin, age, interior, rotation, full chemistry, lives in the margins we haven't filled. That is not a flaw in the story. It is why the story continues. What we know is enough to plan. What we don't know is enough to care. Not just messengers, couriers. A body like 3i, Atlas, carries more than motion. It carries inventory. Water locked in pores, carbon-bearing ices, dust mantles seeded with simple organics that disks synthesize as naturally as frost. When sunlight touched it, we didn't hear a greeting. We heard materials in transit becoming legible 08 at 18 centimeters for water, a volatile balance hinting at colder storage than most of our reheated comets. The point isn't romance. It's logistics. If this traveler reached us intact after long exposure to deep space, then moving chemistry between stars is not hypothetical. It has at least one working channel. This is the sober version of lithopanspermia, the idea that solid material can ferry the ingredients of life and, in extreme formulations, even dormant life, across interstellar distance. You don't have to claim passengers to see the vehicle. Start upstream, in a newborn system. Planetesimals collide, giants migrate, resonances pump orbits, debris gets ejected. Some of that debris is rubble, some is ice-rich and porous, some is crusted rock with pockets that self-shield from radiation. A fraction clears escape, enters the field, and cools to tens of Kelvin. The calendar turns by millions of years. Another star's gravity wells, at a lucky angle and energy, invite a pass. Most fragments miss everything. A few skim the outer architecture. Kuiper Belt analogues, scattered clouds. Fewer still fall toward a warm zone where chemistry wakes and delivery becomes possible. Delivery has more than one mode. Dust-scale exchange. Even without big bodies, star-forming regions share dust. Winds, supernova shocks, and gentle cloud-cloud mixing sweep carbon-rich grains through the same volume where multiple systems are forming. Those grains carry PAHs, nitriles, alcohols, small organics that disks routinely assemble under UV and cosmic ray processing. The scale is microscopic. The throughput is enormous. Over time, local stops meaning much for the simplest precursors, pebble and shard exchange. Where stars form in clusters, escape velocities are low, and relative speeds between neighbors are modest. Ejected debris doesn't have to cross half a galaxy. It may only need to drift a few parsecs before another system snags it temporarily, slows it, or grinds it down. The probability is still small per object, but clusters mint staggering numbers of objects. Small probabilities times huge counts become statistics you can't wave away. Cometary couriers. Comets are the heavy lifters for water and volatile organics. Ice is both cargo and shielding. Centimeters to meters of overburden can attenuate UV and charged particles, allowing sensitive molecules to outlast the trip better than they would on a bare rock. When a comet finally warms in a new system, it doesn't need to land to matter. Outgassing feeds a coma where sunlight and collisions rewrite chemistry, and dust grains lifted from the surface can drift across atmospheres and rings, or settle into debris belts that eventually accrete elsewhere. If impact happens, energy is high but porous, volatile-rich projectiles can cushion shocks, preserving a fraction of complex organics in sheltered pores. We've seen this logic locally. Meteorites and gently captured interplanetary dust carry amino acid analogues and sugars formed prebiotically. The same physics scales outward. None of this says life rides easily. It says ingredients move. Survival filters are brutal. Radiation breaks bonds. Time grinds surfaces. Heating near stars unzips fragile chains. But filters don't erase all signal. Shielding exists. Cross-sections are large. Cold storage is long. For complex chemistry, you don't need every chain to survive. You need enough to tip a local soup toward richer prebiotic catalogues than a lone system might assemble on its own. 3I. Atlas is part of that ledger. Its radio line told us water was on board. Its CO2 balance suggested long, deep cold. Its outbursts and morphology painted a porous, layered interior, exactly the sort of architecture that can carry and protect chemistry. It didn't have to touch Earth to participate in mixing. Passing through the inner solar system, it shed molecules and dust that merged with ours, just as our comets do when they cross a planet's sky. On geologic timescales, such transfers are background processes, quiet, cumulative, and indifferent to borders. The mixing isn't symmetric or constant. It depends on the environment. Young clusters, exchange rates highest, distances small, velocities low, opportunities frequent, field stars, exchange slows, distances grow, but the long tail of time and the sheer number of ejecta keep the channel open. Spiral arm structure. Passing through dense gas regions increases collision and capture probabilities. Quiet inter-arm stretches reduce them. That spatial and temporal structure is not philosophy. It's a map we can build. As Discovery pipelines stabilize Rubin for early detection, NEO Surveyor for size, SKA class arrays for OH, and other lines we will turn anecdotes into distributions. How often interstellar objects arrive, from which longitudes, with which volatile ratios, at what speeds and inclinations. If the galaxy is mixing vigorously, the sky will tell us by numbers, not by stories. What would constitute strong evidence for chemical transfer in practice? 1. Capture statistics. A measured fraction of interstellar objects should become temporary satellites of the Sun for months to years, before departing time enough to share dust and gas throughout the inner system. 2. Compositional fingerprints. Ratios or isotopic signatures, where measurable, that cluster differently from native comet families would mark imported inventories. We don't yet have D, H, or noble gas baselines for interstellar visitors. That is a future instrument goal. 3. Correlated deliveries. In young systems, bursts of volatile influx coincident with external perturbations, nearby passages, cloud encounters, would argue for episodic enrichment from outside reservoirs, not just internal rearrangement. Skepticism belongs in the same paragraph. Mixing is real. Biological transfer is unproven. Dormant organisms surviving interstellar timescales remain an open research question with physical and biological hurdles. this section doesn't smuggle in life. It stays with prebiotic logistics. Interstellar bodies can move water, carbon, nitrogen, and simple organics between systems, and we have now observed at least one such body doing the first half of that sentence in ours. Why it matters, even with the caveats, is clear. If multiple stars repeatedly receive imports of water-bearing solids and carbon chemistry, then the starting kit for habitability becomes less parochial. Worlds seeded by both local synthesis and imported catalogues begin higher on the ladder of complexity than worlds relying on a single pantry. That doesn't guarantee life. It levels the field where life could begin. Bring it back to the voice of the series. The motif is not destiny. It is traffic. 3i Atlas wasn't a messenger with words. It was a vehicle with stock. It passed, it breathed, it shed. A tiny amount of that breath joined ours. And out there, in the arithmetic of large spaces, other travelers are doing the same for other suns, all the time, without permission and without pause. We used to picture the solar system as a fenced yard. 3 visitors into this new era. The fence looks more like a membrane selective, leaky, alive with exchange. The galaxy isn't a static backdrop where stories happen in isolation. It's a circulation. It shares. And when we learned to listen at 18 centimeters, we didn't just hear a comet. We heard the quiet sound of mixing, already underway. Call it what it was, a narrow line at 18 centimeters that rose with heat and faded with distance. No cadence, no code, just water meeting light and obeying physics so precisely that our antennas could turn it into numbers. But that narrow line carried weight. It marked a line we crossed, to the point where our instruments and coordination became good enough to hear chemistry from an object that began under another sun. The meaning isn't in the comet's intent. It has none. The meaning is in our capability. We can now detect time and compare events that used to slide by as rumors. Open the mirror to part 1 and read it back. We began with a paradox. We received something, but it wasn't a message. After the orbit solutions, the OH spectrum, the light curve, the anti-tail geometry, the outbursts, and their returns to trend, the paradox dissolves. There was a conversation after all between water, light, and time, and we were allowed to listen because we showed up with the right tools at the right hour. The conversation sounded like this. Light set the clock. Insulation rose toward perihelion. The line followed, then both declined. Breath made the trace. Gas expanded from vents, writing widths in the spectrum we could read as speed. Memory carried the motion. A hyperbola energy positive curved past the sun, unbound in and unbound out. Silence drew the boundary. No modulation, no beacon, only the absence that lets the physics stand alone. Together, those 4 are enough to replace wonder shaped like speculation with wonder shaped like comprehension. We didn't need to embroider the story to keep it large. The scale was already there. Ice, older than our oceans, stored in deep cold, warmed by a star it didn't know, rising to a narrow frequency we could weigh from half a world away. Meaning also arrived in the way the work changed us. The team that built the plan, surveys to find it, astrometry to fix it, radio to weigh it, optics to watch it, has a template now. You can hear the maturity in the verbs. Schedule, stack, calibrate, publish. The next visitor will inherit that discipline. The one after that will refine it. At some point, not far from now, a dashboard graph of an interstellar comet's OH line will feel as ordinary as a weather map. Ordinary in the sense that matters. Available, repeatable, comparable. We couldn't read the isotope ratios we wished we had. We couldn't photograph the architecture that made the cracks and pockets that fed the outbursts. We could only infer. The limits didn't make the detection smaller. They kept it honest. Mystery, conserved correctly, is a working space, not a surrender. If you need one image to close this chapter, keep it spare. A comma of light in a dark frame, a spectrum panel below with 2 small peaks on a baseline, and a thin curve on an ephemeris plot arcing past the Sunday. 3 panes, 1 story. The picture says where, the line says what, the curve says how. No, one says who. That's all right. We learned what the sky was offering and what it wasn't. Then we wrote it down in a way the next object can use. The lesson travels beyond a single pass. If similar chemistry behaves the same under different suns, then comparison becomes the instrument that outlives an event. We can stack lines from future visitors, map volatile ratios against approach geometry, and watch distributions emerge where anecdotes used to stand alone. A field that once had one outlier and one textbook now has a third point and a working standard. This is how speculation yields to measurement, increment by increment, until a new normal appears and the drama moves from claims to curves. So no, it wasn't a message. It didn't try to be heard. It didn't aim for us. It didn't slow to speak. It passed. It warmed. It breathed. And we were tuned well enough to hear the breath. That is the profound part. The universe didn't change its language. We learned enough of it to catch a word. Let that be the calm at the end. We are not waiting for intention to feel addressed. We are learning to take meaning from invariance frequencies that don't shift with belief, curves that don't flatter bias, lines that appear when a molecule has no other choice. Between water, light, and time, there is now a place for us to stand with an instrument and say, "We heard you," and mean nothing more supernatural than a measurement done correctly. The sky will send others. Some will be louder. Some will whisper. We will be ready to be changed by either, not by what we imagine into them, but by what they make audible when our star does its ordinary work and we do ours. The sky never closes. It only exhales. Somewhere beyond Neptune's slow blue orbit, a point we cannot yet name is pushing against the background, faint, lawful, inbound. It doesn't know we exist. It doesn't aim. It travels because momentum remembers. What changes this time is not the traveler. It's us. We have a lane now. Surveys sweep and differencing locks onto motion. Brokers push alerts in minutes. Orbit solvers test energy signs before the rumor hardens. If the fit goes unbound, the board lights up astrometry from multiple longitudes. Precoveries mined from last week's frames. Uncertainties collapsing by the hour. We will have days, not scraps, to plan the listen. When the ephemeris says the heating will bite, the radio will already be booked. The 18-centimeter window is not a hunch anymore. It's a standing order. Arrays will Doppler track in the object's frame, stack clean channels, and let a narrow line crawl out of the noise. If water is there, it will announce itself with no need for headlines. Infrared time will bracket perihelion for CO and CO2, so we can put volatility on a clock. Who turns on first? Who lingers? Who tells us the storage history? Optical teams will map morphology and catch geometries, tricks, ion tail, dust tail, and, if we get lucky with an edge on pass, that sunward spike through the dust sheet that looks like intent, but isn't. 3 bands, 1 playbook. The wonder is not that it's possible. The wonder is that it's ready. Rubin will make earlier. Its cadence and depth will lift faint streaks over the threshold while they're still only whispers. Neo Surveyor will stop us guessing sizes by albedo. Well know diameters when it matters, not after the fact. As SK mid scales what Meerkat proved, 18-centimeter OH becomes routine even for shy comets, and weaker lines step into reach. The first time felt like a proof. The next times will feel like coverage. This is the part most people miss. Anticipation is a tool. Knowing another is coming changes how we schedule, how we archive, and how we talk. The first public statement won't be a verdict. It will be a plan. Here are the windows. Here are the checks. Frequency, timing, shape. Here is where weird would have to live to count. That transparency is not theatre. It is guardrails against our own appetite for drama. When the antitail appears, we will show the geometry in the same frame and let the projection do the explaining. When an outburst spikes, we will put a dot on the light curve and ask the radio to tell us whether water followed. When the line fades, we will call it by its correct name. Less sun on the surface, less breath in the beam. The motifs that carried this story do not change at the end. Light will still set the clock. Breath will still make the trace we can weigh. Memory will still be the part of motion that does not negotiate. Silence will still mark the boundary between signal and wish. Another inbound object won't break those. It will pass through them, and well measure how. Some visitors will be austere, dust-poor, coma-shy, sliding past with only the faintest chemistry to hear. Some will be loud, fractured, vented, extreme in ratio and rhythm. A few will arrive at awkward angles or behind the sun, and well have to lean on spacecraft imagers and heliophysics instruments to keep the thread. A very few will refuse our categories. and those will be the ones who teach the most. The point of a standard is not to flatten the sky, it's to know when the sky isn't following it. Another is coming can sound like a promise of spectacle. It's a promise of work. The work looks like people at screens when most of the world is asleep, pointing dishes into a quiet band, rejecting interference, stacking hours into lines. It looks like coders are hardening a pipeline so streaks don't slip past. It looks like a coordinator tapping out a schedule that survives weather on 3 continents. It looks like a data steward who labels everything so a student 5 years from now can reproduce an argument without calling anyone. If the last object made us better, the next will make us rigorous. There's a softer reason to be ready. The first time we heard 18 centimeters rise on schedule, we traded rumors for numbers. The second and third times we'll trade numbers for comparisons. That's how a field grows a backbone. Interstellar stops being an exception and becomes a population with scatter and trend. The ore doesn't leave. It moves. It lives in a plot that starts to bend where theory said it would. And in the moment a curve deviates and tells you you've found the edge of what you thought you knew. If you need a closing frame, keep it small. A blank patch of sky. No comet yet, just the place where one will be. In the corner, the outline of a dish. On a monitor out of view, a spectrum with nothing in it for now. This is the posture the new era asks for. Listen, before there is anything to hear. When the dot finally enters the field, the rest is procedure. And procedure is how you turn a rumor into a record. The signal wasn't a fluke. It was a doorway we walked through by learning the molecule's language and showing up on time. On the far side of that doorway is not a stage for messages, but a corridor of future work. Earlier detections, cleaner orbits, tighter schedules, quieter receivers, better archives, honest summaries. The universe doesn't whisper to us. It whispers through matter. We have ears for that now. Another is coming. Maybe not brighter, maybe not a stranger, but it will be enough. We will aim, listen, measure, and add one more line to the chart that outlives our surprise.